Was saying this is intended to give you an example of how you would approach a real-world data set from start to finish. This is probably going to be a bit, well, this is definitely going to be a bit longer and a bit more detailed than what I would expect you to do for your project, so don't freak out and think, oh, there's no way I could do anything like this. I mean, if I just did a quick little 5-minute thing that's one t-test, that wouldn't be as interesting. But, I mean, for your project, any sort of reasonable analysis on a reasonable data set is fine. But, anyway. So this was a data set from a student in this class a few years ago, and, oh, it's really interesting. It's projecting in presentation format, so you can see my next slide and the amount of time I've taken. It's not supposed to project like that, oh well. But at any rate, in this study there were she worked in a lab that did a bunch of work with liver cells. There were 3 culture systems. Each culture system had 12 sample wells, and in each system there was a different flow rate, 0.4 milliliters per minute in one system, 0.3 milliliters per minute in another, and 0.2 in the final system, and each well contains one of 3 types of media that were called R, F, and G, and LDH was measured in each well over a period of 6 days, and honestly I don't know what RF and G stand for, nor do I know what LDH stands for that matter, but for the purposes of this example it doesn't really matter. So the main question she was interested in was, does LDH level vary according to flow rate, and does it vary according to media? And things like day, and day is basically just a confounding variable in this case. So if you've looked at my lecture 22 with the review with just kind of a checklist of items to consider when approaching this type of problem, the first thing to do is just kind of look at what variables you have. Think about what your response variable should be, if it makes sense to denote a variable as a response variable. Think of what other variables you have and figure out whether they are categorical or quantitative. So LDH is clearly quantitative and it's the outcome in this case. We have media that is clearly categorical. It has 3 possible values, R, F, and G. And day and flow rate are putatively quantitative, but day only has a finite number of possible values, 1, 2, 3, 4, 5, and 6. And flow rate also only has 3 possible values, so potentially we could model them as categorical if we wanted to, and if it looks like there's a nonlinear relationship between the variables, maybe it makes more sense to model them as categorical. So the first thing I recommend that you do in all these types of things is plot the data. It's a good way to identify outliers, and it'll give you an idea of the overall pattern. Well, you can already see the next slide why plotting the data turns out to be crucially important in this case. By the way, for this presentation, I'm inserting the R commands, so if you want to try this on your own, you have the R commands that I use to create this. For your actual presentations, you don't need to, and in fact, I discourage you from posting the R commands in your slides, just in the interest of getting through this in a reasonable amount of time. Just posting the plot will be sufficient. So here's a plot of LDH versus day, and this illustrates immediately why it's a good idea to plot your data. You see that the relationship over time isn't really linear, but it's actually fairly close to linear if you throw out day 1. And also if you look at day 1, there's all kinds of crazy outliers. The LDH levels are all over the place, whereas once you go past day 1, then things are bunched much more tightly together. So you'll see here in a sec, I just basically decided to exclude day 1 from my analysis because it doesn't fit the pattern of the remaining days and it's also kind of messy. Here's a plot of LDH versus flow, and as I thought about this, this probably isn't the best way to plot it. That doing a side-by-side box plot probably would have been better because you could have. It's really hard to visualize what the mean, median, and other summary statistics are on a plot like this, but you know, whatever, it works, I guess. So based on these plots, we see that LDH varies by day, although the pattern isn't linear overall. It does look like it's linear from day 2 onward, and we don't see much of an association between LDH and flow rate. So in this case, our response variable is quantitative. Our predictor variables are partly quantitative and partly categorical. So in that case, we would use ANOVA/ANCOVA. I didn't really discuss ANCOVA, but as I said, ANOVA is just basically a form of regression with dummy variables. ANCOVA, or analysis of covariance as it's called, is just a regression model that includes both dummy variables and quantitative variables. That's very easy to do in R, as you'll see in the next slide. You just do a multiple regression model that includes both quantitative and categorical variables, and R does it automatically. So it sounds really fancy and intimidating, but it's really not. So the first thing I tried was fitting the model using the full data set, and just to avoid confusing people later on. This was deliberate because for the purposes of this problem, if we want to control for the effect of day at the bare minimum in all these analyses, and probably the effect of flow and media as well. Generally speaking, you should not do a multiple regression model first like this. If you want to know if flow is associated with the outcome, you do a regression on flow individually and then media individually and so forth. In this case, we know that we want to control for the confounding effect of day and everything, which is why I jumped immediately to the multivariable approach. But for your projects, if you just have a list of possible variables possibly associated with the outcome, you should do regressions one at a time, or do t-tests or chi-square tests on each variable one at a time before you do this multiple regression model. And you look at this big model, and it looks like the experiment's kind of a bust. There's an effect of day. Well, okay, who cares? We don't see any effect of flow or media, which was what we were really interested in. But like I said before, day 1 doesn't fit the linear pattern. It has tons of outliers that may be skewing our results. Let's just scrap day 1 and try this again. It's the same model, I just added the subset command in our, say, subset day greater than 1. That means take everything where the day is bigger than 1. And once we do that, suddenly this becomes a lot more interesting. The effect of flow rate is significant, as is the effect of media G. There's still no difference between media R and the baseline, which I believe is media F in this case. So it looks like a higher flow rate's associated with higher LDH level, and the medium G is associated with a higher LDH level. But let's look at this a little more closely to see if that's the full story. Let's plot LDH versus flow rate again and exclude the data from day 1. There's the R command you would use to do that. And now, I mean, again, I really should have done a side-by-side box plot here because it would be easier to see. If you look at the rightmost group, you can see it's shifted up just a little bit from the other two groups. That would be easier to see on a box plot, but oh well. I noticed this at about 4 in the morning last night and decided that getting at least a couple hours of sleep was a higher priority than making my slides perfect. So anyway, There's some evidence that a flow rate of 0.4 may be associated with higher LDH level, but we don't see a lot of difference between 0.2 and 0.3, so that suggests to me maybe we should model this as categorical rather than continuous. There's only 3 possible values, so you could treat it as categorical. If there's no difference between 2 and 3, but there is a difference between 4 and the other 2 groups, maybe we should do it as categorical. And we do that, and yeah, sure enough, according to the new model where we treat flow rate as a factor, at flow rate of 0.3, we don't see much of a difference. Well, I guess one advantage of the fact that it's projecting weird is that I can use my mouse to point. No, we don't see much of a difference between flow rate 0.3 and 0.2, but there's a big difference between flow rate of 0.4 and 0.2 and 0.3 by extension. And same story before, the media G is also associated with a higher LDH level. So it looks like our conclusions from looking at the graph were correct, that only the flow rate of 0.4 is associated with higher LDH level. These last couple slides, I didn't teach you about interactions in this class. I cut this material as I shortened this course to 10 weeks. So if you want to just fall asleep for the last bit of this presentation, you're welcome to. This definitely isn't going to be on the homework, nor am I going to expect you to do it for your projects, but it's kind of cool, and I thought I would at least show you what's going on in case you ever have your own data and you want to play with this. And I mean, if you're an overachiever and want to try to do this on your project, by all means, but I recognize this isn't something that I taught you. That the idea behind interactions is, in brief, that can two variables combined give you more information than a single variable. For example, is it possible that if you have a flow rate of 0.4 and you're in media G, that the LDH level is higher than you would expect just adding the individual effects, if that makes sense? That the graph might make this a little clearer. That the first plot here is flow by day interactions and basically shows the flow rate and basically shows the mean level of LDH by both flow rate and day. If there's no interactions, you would expect these lines to be more or less parallel, and for the most part they are, but this one line, I think that's day 1, which day 1 was the weird day to begin with. There's some indication that for, with the exception of day 1, it looks like flow rate tends to decrease, or that LDH tends to decrease over time. The lines are more or less parallel, but day 1 we see this weird pattern where the LDH level is really low for a flow rate of 0.4, but generally fits the pattern 0.2 and 0.3. Here in a minute I'll show how you formally test this. Here's the flow media interactions, again showing the mean LDH level for each flow rate for each different type of media. Again, no interaction, we would expect them to be parallel. And at 0.2 and 0.3 they are more or less parallel, but it looks like for media F seems to have higher LDH levels at flow rate of 0.2 or 0.3, but much lower LDH level for a flow rate of 0.4, so possible interaction there. Finally, the media by day interactions, the main place where they seem to be non-parallel is for media G days 5 and 6. It looks like for media F and G, the LDH levels tend to decrease over time, but for media G, the LDH level doesn't decrease quite as much at days 5 and 6 as we would expect to based on the pattern in the other groups. So here's a command in R to test for interactions. If when you do a formula object in R, if you say day star flow star media rather than day plus flow plus media, that includes all possible interactions. So the day flow interaction, the flow media interaction, the three-way day flow media interaction are not significant, but the day media interaction is strongly significant in this particular table. So that suggests that maybe we should include an interaction term between day and media in our model. So, I mean, it's based on the graph, it's possible if we had included day 1 that we would have seen some additional interaction terms, but we didn't, so we don't. So, our final model will just include the main effects plus an interaction for day and media, and our final model looks something like this, that consistent with what we saw before, that a flow rate of 0.4 is associated with higher LDH, media G is associated with lower LDH, and there's this day media interaction that if you have media G, the LDH level doesn't decrease quite as much at day 5 and 6 as we would expect. So the basic conclusions that we come to based on this data is that the LDH level decreases over time, with the one exception from day 1 to day 2. The system with a flow rate of 0.4 has higher LDH levels, and medium G, generally the LDH levels are lower, but they don't decrease as much over time as it does in the other two types of media. In particular, at day 5 and 6, the LDH level tends to remain about the same as it did at level 4 rather than decreasing. So